All right, so last section of chapter 4 is going to be a pretty short one here. It is talking about the coefficient of determination. All right, so what is the coefficient of determination? Well, first off, it is r squared. So if r is the correlation coefficient and we square that value or times it by itself, we get the coefficient of determination. And it measures the proportion of total variation in the response variable that is explained by the least squares regression line. We have a value that is going to tell me the proportion is going to turn into a percent of the variation, how it is related to the least squares regression line. So this value is going to be between 0 and 1, meaning that 0 has no explanatory value, and 1 means the line explains 100% of the variation in the response variable. Let's see if we can make this make a little more sense here. We have our predicted line here, and we used our predicted line to get when we put in 103, we got at 270.3. That's what we were supposed to get according to our equation. And what we actually got was 274 there. What they've drawn in the middle here, this line is the average of the y values. So we have some things that happen here. So this distance from the average up to the line is what we've expected to happen. We expected from our average to go this much. This difference is explained by our club speed. Now, because we've gone above here though, and my actual is up here, this difference is unexplained. We don't know why this one went a little bit further. Again, we knew at this point, our average distance that we hit from 99 miles per hour to 105 miles per hour was 266.75. Our equation told us that we should get, with a speed of 103, we should get 270.3 darts. That makes sense. That is explained by our equation using the least squares regression line. Okay, but this difference here is unexplained. If we know that the club speed is 103 miles per hour, we increase our guess to 270.3 yards. That's according to our equation. The difference between the predicted distance of 266.75 and the predicted distance of 270.3 yards is due to the fact that the club head speed is 103 miles per hour. In other words, the difference between the prediction of using the value of the equation and the average value is explained by our equation, that linear relationship that we have created. All right, that is what we created this equation from. The observed distance, though, was 274 yards. The difference between our predicted value of 270.3 and the actual of 274 is due to factors other than the club head. Maybe it was wind speed, maybe it was position of the ball, maybe on the ground. It could have been, was it on a tee, was it on the ground, position of the ball in the club face, did I hit it at a different part of the club? So many other things that could have impacted my shot to go a little further. Okay, it's called a deviation. It is further away than what we expected to happen from average. Again, here is our average value. And as I go here, these distances are the same all the way across here. I am expecting this to be about as far as this is. Those deviations here between what the average is and what our line says are explained by the fact that slower should go less. Anything outside of that, so this is further away. Something happened to make this not go as far. So there's some sort of unexplained reason here why this one didn't do as good or why this one did better. This one's even a little better too. So there's some unexplained reason why those got a little better or a little worse than what should have been. When we are working with a coefficient of determination here, everything we're doing is linear regression. We are going to square the linear correlation coefficient, okay? Just a note that this doesn't work for other models, but we're not working with other models, so this is what we're gonna get. So capital R squared is the coefficient of determination, which is calculated by doing little r squared, or the correlation coefficient squared. So here's what we're going to do, just to kind of explain the topic a little bit more. I've got 3 different data sets here, A, B, and C. Okay, each one is going to have its own set of data here. If you look at A is darn near perfect sort of relationship here. B is still a pretty strong relationship here. C, I would say, is a pretty weak relationship. There's not a whole lot of relationship here that's happening. There's a lot of values kind of all over the place. What's going to happen here is the R values are going to give you almost perfect, pretty strong, really weak. So when I take those values and I square them, I'm going to get another value. So the R squared in this first one is 99.9, or sorry, we're going to get R squared equals 0.9999. This one's going to be R squared is 0.947. This one's R squared is going to be 0.094. Okay, so what we said is it can go anywhere from 1 to 0, 0 to 1. And the closer you are to that 1, the line explains the variation in the y's. Here's how we would explain that for each of these. So in this one, we would say 99.9% of the variability in y is explained by the least squares regression line. So really, this line is about 99.9% accurate in predicting my values. This one here, when I get R squared of 0.947, 94% of the variability in y is explained by the least regressions line. Okay, 94% accurate. So most of these are within normal understanding of y, where they should be. There's a little bit of variation here that's outside of the normal, but it's not a whole lot. There's still about 94% accuracy with this line representing the data and predictions. Here, if you look at 6, my value is down here and it's supposed to be up here. Okay, I am so far down. I am so far down, so far down, so far down. But then I've got all these up here that are so far up. So because this relationship wasn't very linear to begin with, it wasn't a very strong relationship, the line is not going to be very accurate in predicting what we want, which is why the R squared value is so small. So we got 0.094, close to 0. 0.094 is 9.4% of the variability in Y is explained by the least squares regression line. So quick recap here. If you are given the decimal 0.999, how do I turn it into a percent? You just times by 100. So times by 100 gets you here. Times by 100 gets you there. Times by 100 gets you there. Okay, so when you run your statistics, it will come up as well. It'll come up as R squared, and then you just have to write your sentence. So whatever your percent is, and then fill in the line of the variation in distance is explained by the least squares regression line. So 88% is explained by the regression line. That leaves 11.8% of that variation is from some other factors. We don't know what those factors are, but there's some other factors that are playing into part of these results. I'm going to open that data set again here. So I'm going to redo the results quick. Stat, regression, simple linear. X is length, Y is weight. So again, this one wasn't super strong. Okay, it was set, the correlation coefficient was 0.70. R squared is going to be right below it. 49, so 0.495, if I move that decimal times by 100, move it back 2 places, 49.5% of the variation is explained by the line. That means about 50% of it can be explained, and 50% of it, we don't know why these values, there's other factors, other lurking variables, things that are impacting the weight based off of the length. Whatever's remaining, whatever the remaining percent is your other factors that are impacting these values to be so far away from what they should be. We can always allow for a little bit of deviation, but when they're really far apart, then clearly there's other things that are impacting that data. Let me see if we can find another one here. Square footage of a house and its selling price. I'm assuming that this is in thousands. So 379,900, I'm going to guess. We go again, regression, simple linear. The square footage should determine the selling price of my house. Kind of recapping here, I have my equation. My selling price can be calculated by 14.87 plus 0.156 times square footage. I have 12 values. Here's my correlation coefficient, 0.9. Okay, so it's gonna be pretty strong. My data is pretty close to the line. I've got an 81% here of R squared. So 81% of the variability of Y can be explained by the line. There is a, what would leave 19% that is, the variation is explained by some other factors. Some of this variation here can be explained by the line, but some of them, there is probably some other reason why they're a little further away from what they're supposed to be. It could be a different neighborhood. It could be what upgrades you have, finishes in your house. Trying to think. Those are the top 3 things I could think of. And what would make your house sell for either higher or lower? Renovations, roof, recent roof, air, like any of those kind of things. Is your heating and air replaced recently? Any of those things could be added factors into this. Those other kind of lurking variables that could impact why these values were maybe not as close to the line as they should be. We can talk about the slope here. So for each additional square foot, we could expect our price to increase by $156,000. if that is that these are in thousands of dollars, I believe. Okay, so this section was really short. I hope it makes sense here. It's just a matter to explain. I think this one explains it the best here. That is the percent of variation that's explained by the line, which then leaves what's left. So if 88.1% is explained by the line, 11.8% is explained by some other factors. And that could be different things. Like in the golf club problem, we said it could have been due to wind speed, position of the ball, and of error. There's so many other things that can impact our results. All right, so that is section 4.3. If you guys have any questions, remember to reach out to me via email. And I will see you back here at chapter 5.